Hello, and welcome to the 2020 Lawrence Award ceremony. I am Dr. Katie Schroeder-Spain, the Lawrence Award Program Manager, and it's my pleasure to welcome you here today. I would like to say a special word of welcome to the Department of Energy's leadership in attendance today, as well as a welcome to the DOE National Laboratory Directors, the laureate nomination teams, award peer reviewers, and of course, our laureates and their families and invited guests. Now it's my pleasure to introduce Energy Secretary Dan Brouillette, who has provided us with pre-recorded remarks.
Good afternoon, everyone, and welcome. Today, as I conclude my time here as Secretary of Energy, I feel especially fortunate to be honoring some of the most gifted and creative minds in our country with the 2020 Ernest Orlando Lawrence Award. These are people whose vital and path-breaking research we've had the privilege to support here at the department. Representing universities and national laboratories, they're responsible for achievements across a remarkable range of disciplines: atomic, molecular, and chemical sciences, biological and environmental sciences, computer information and knowledge sciences, condensed matter and material sciences, energy science and innovation, fusion and plasma sciences, national security and nonproliferation, and of course, nuclear physics. Each of these recipients has made major, pioneering advancements in their respective fields. They follow in the footsteps of a truly pioneering scientist for whom this award has been named. Ernest Lawrence was a key architect of America's leadership in science and technology. Established in his honor in 1959, the award bearing his name is among the nation's oldest and most esteemed awards. It honors American scientists and engineers at mid-career for exceptional contributions in research and development, supporting the Department of Energy and its mission to advance the national economic and energy security of the United States. And so to all of our 2020 Lawrence Award recipients, I offer my heartfelt congratulations on behalf of a grateful department. We appreciate and honor your phenomenal accomplishments and look forward to your future successes. Thank you.
Thank you, Secretary Brouillette. Now it is my pleasure to introduce Undersecretary for Science, Mr. Paul DeBar, who has also provided us with pre-recorded remarks.
Thank you. I echo the Secretary's words of praise and commendation to all of today's Lawrence Award recipients. I could not be prouder of their achievements, and as a member of the leadership team of a department whose innovation missions depend on science and technology, I appreciate their successful efforts across this vast and exciting landscape. Through our system of 17 national labs, DOE supports scientists and provides world-class facilities and tools from supercomputers to X-ray light sources to ensure America's leadership in science and technology, which remains vital to our continued security and prosperity as a nation. If we are to appreciate just how prestigious the Lawrence Award is, we need to say a few things about Ernest O. Lawrence. In 1939, Lawrence was awarded the Nobel Prize for inventing the cyclotron, the world's first particle accelerator. He went on to play a major role during World War II in the Manhattan Project. But that's not all. After the war, he was a major force in the establishment of our entire national lab system, and through it, the tremendous growth and expansion of the American scientific endeavor. In fact, 2 national laboratories in California, Lawrence Berkeley, which grew out of Lawrence's own radiation laboratory at the university, and Lawrence Livermore bear his name. That's the kind of man Lawrence was, and that tells us all we need to know about the caliber of people who have honored today through the Lawrence Award. Thank you.
Thank you to Undersecretary DeBar. It's my pleasure now to introduce to you live Dr. Chris Fall, Director of DOE's Office of Science. Dr. Fall?
Live and in person, except for it's virtual. Thanks, Katie. Thanks to the Secretary and to Undersecretary DeBar for their remarks. It's a lot of fun to work for folks who are such, really great supporters of science and technology, and they are. Before I forget, I do want to thank Katie Schroeder-Spain for directing, and Talia Meltzer for a strong assist in leading the team that shepherded these award packages and then arranged this virtual ceremony on very short notice. The reviewers that helped us make the tough calls on the laureates. Months and months of work under the difficult circumstances that we all can appreciate and are obvious to everyone. So thanks to you all for joining. We have 217 folks, it looks like. Well, thanks anyway to colleagues, friends, families, and other guests. Maybe I don't need to thank the laureates for attending their own ceremony. But as director of the Office of Science, I'm so pleased. The Office of Science team, the other represented components of the Department of Energy, we were all incredibly thrilled that we could get this ceremony over the line on such short notice. And I can't tell you how happy it made me to be able to call the 8 laureates a couple of weeks ago with the news. I think I surprised a couple of them. There are really 2 things that I cherish about this job besides the phenomenal people on our team here at the Department of Energy. One is getting to visit the laboratories and to meet researchers and see world-changing science happening. Note that I say see world-changing science happening. They never actually let me touch anything when I visit the labs. Probably better that way. But the other is being able to recognize great contributions, right? To the Office of Science, from my team to the department. It takes a lot more than phenomenal scientists to make this enterprise run. But really the best fun is to be able to recognize the folks that hit the balls out of the park when it comes to science and technology. That's, one of the 3 core missions of the Department of Energy. And the only reason that those of us in the Department of Energy exist in our jobs is to provide the resources, the labs, the facilities, the organizational frameworks to create the conditions that can make these achievements possible by the phenomenal talent like our laureates. So, besides that, I got to tell you, it sure feels good right now to be able to celebrate achievement. As the Undersecretary said, the Lawrence Award is one of the most prestigious awards given by the U.S. government. It was created by Eisenhower himself on Lawrence's death back when science and scientists loomed maybe a bit larger in the public consciousness. The age of Fermi, the age of Oppenheimer, and Lawrence. And by giving these awards, we're, to be sure, we're honoring the laureates and undersecretary their accomplishments, but we're also remembering and honoring Lawrence. Let me echo the Undersecretary. What's so special about E.O. Lawrence? Well, at the end of the day, he put the big in big science, right? He put the scale in what we now call science at scale. But it's really important to understand nuance here, and that's that his profound contribution wasn't so much about just going big. We have a tradition in this country of the individual investigator at a university. We cherish that tradition. I was one of those. Sort of the idea of genius in their lab or maybe in their basement. That's a very American thing. The model there is that we'll give you some modest money each year and you'll make whatever progress you can with that. We'll give you some more money the next year and so on. This provides stable careers for scientists, great science to be sure, but it's generally more incremental, especially when it comes to experimentalists, because the sort of, one size fits all model that we have, more or less in terms of the resources that are handed out. And what Lawrence did, the important thing that he did was to flip the script on how we approach scientific questions. Instead of saying, here are some resources, go do what you can with them, he said, here's the question we want to answer, the questions that we want to answer. And in order to answer those questions, we're going to need this thing, maybe something really big, literally, really big. Behind me is the building where some of his original equipment was housed at BN at Berkeley, or maybe really big budget-wise. because the questions that we want to answer simply require that scale, right? These machines have and do require big teams of interdisciplinary scientists and engineers to make it all work. They are oftentimes world unique, and so they attract talent from around the world to do science, require longer term planning, frankly, deft advocacy to political leaders for support. It's an attitude of go big or go home, as they say, and it really represents the foundations of the essential thing that the Department of Energy provides for the nation today: science at scale. Start with the problem we want to solve and do it the right way. Concentrate resources to make that happen. Try not to compromise on the science. Do the kind of science, answer the kinds of questions that befit a great nation. That's the transformation that Lawrence wrought. Yeah, I'm simplifying things a little bit. Sure, a whole lot of other really special people have shaped the Department of Energy mission in science and technology. Lawrence certainly had peers that helped shape his thinking and allies in Washington and other places. But if you had to pick one, he's not a bad pick, right? Nobel Prize at 38 for the cyclotron in that building, looking down, formed the foundations of Lawrence Berkeley National Lab and supported the creation of Lawrence Livermore National Lab. The Undersecretary mentioned that. One of those giants back when science captured the imagination of the public, right? He didn't just discover new physics. I think most of us would be satisfied with a new discovery or two, but he fundamentally changed how we do science in this country and really the world. So Lawrence's head is on the medals that you all are going to receive today. I'll show you one because there you go. They look like this. Oops. Now my virtual background is, there we go. Pretty good. It's a good thing you're not in DC and we have to ship them because these things are heavy, you know, real simulated gold. Probably wouldn't get them through the metal detectors at Reagan right now, I'm guessing. But wait, there's more. For your profound contributions, you also get there we go. You can sort of see it in the virtual background. A certificate made of genuine paper. You laugh, maybe, but these days, how often do we really get to touch real paper anymore? I haven't signed a paper document for the Department of Energy since March. Your certificate will come in this engraved leather. Sorry about the camera. There we go. Engraved leather binder, also with, you know, Lawrence's head on it in real, less real looking simulated gold. And a nice lapel pin for you there. Let's see, simulated gold Lawrence medal, fancy engraved certificate and binder. There's something else. Oh, yes. But you guys don't care about the cash, right? Yes, you get some cash, presumably not on genuine paper, but it's kind of unseemly to talk about the money, and we're pretty sure that that's not what's motivating you. Nice to have, but that sort of thing never really is the motivator for things that really matter. But speaking of motivation, this is a, you know, formally, this is a mid-career award. We'd like to think of it as a down payment. We're betting that despite all of your achievements already, each of you might have some of that Lawrence spirit in you. And by the time you're done, some of you might leave your fields transformed the way that Lawrence has transformed physics. What we know, yes. How we do science, maybe, or maybe even both. So no pressure, right? All right, so speaking of what matters, let's move on to what matters here, and that's you all and your awards. Before we get to that, and before your heads swell too much, just a word to say that, you know, in fact, there were a lot of nominees for these awards, and there were some close calls and hard decisions, as I alluded to before. The good news for you is that, the 8 of you is that you won the awards this year. The good news for us in the Office of Science is that there's an awful lot of great science and technology being done and competition for the future, more potential Lawrences out there. But today is for the 8 of you and for the colleagues, friends, family who've joined us here virtually at the DOE to celebrate you. So let's get on with that. Katie, what do we have next in store for our 8 laureates?
Thank you very much, Dr. Fall. It's now my pleasure to welcome each laureate to our virtual stage. As I introduce each laureate, we will also take a photo of the laureates with Dr. Fall, who will read their award citation.
That's not going to work.
You'll see. And confer each award on behalf of the Secretary of Energy. So up first, in the category of Energy Science and Innovation, Dr. Etoy of Stanford University and SLAC National Accelerator Laboratory. Congratulations, Dr. Etoy.
Thank you.
Should I like hand the virtual medal or hand the medal over to you virtually? Sorry, we're reversed. I'm actually looking at you.
You could, but it's now your cue to read the citation.
Here, I'll virtually, even though the camera's not working, hand over the medal to you. But now I have to face the other way. This is really awkward. Maybe that's not going to work so well. Let me read the citation. I have to put my glasses on. For exceptional contributions in nanomaterials design, synthesis, and characterization for energy and the environment, particularly for transformational innovations in battery science and technology. Congratulations.
Thank you.
Up next, in the category of National Security and Non-Proliferation, Dr. Dana M. Dattelbaum of Los Alamos National Laboratory. Congratulations, Dr. Dana Dattelbaum.
Dr. Dattelbaum, for pioneering physical insights into shock and detonation physics, innovations in the development of equations of state for energetics and polymers, and critical data for hydrodynamic simulations essential to the national security programs. Congratulations.
Thank you.
Up next, in the category of Fusion and Plasma Sciences, Dr. Dustin H. Froula of the University of Rochester. Congratulations, Dr. Dustin Froula. Dr. Fall?
Dr. Froula, for innovative research in laser plasma physics, including pioneering spatiotemporal pulse shaping techniques, focused laser plasma instability research, and novel high-resolution Thomson scattering methods that have significantly advanced the Department of Energy's mission. Congratulations.
Thank you very much.
Up next, in the category of Condensed Matter and Material Sciences, Dr. Zaheed Hassan of Princeton University and Lawrence Berkeley National Laboratory. Congratulations, Dr. Zaheed Hassan. Dr. Paul?
Dr. Hassan, for groundbreaking discoveries using spin angle resolved photoemission spectroscopy, which elucidated the topological nature and electronic structure of topological insulators, topological phase transitions, and topological semimetals, while fermions, revealing them as new phases of quantum matter. Congratulations.
Thank you.
Up next, in the category of Nuclear Physics, Dr. Daniel Cason of the University of California, Berkeley and Lawrence Berkeley National Laboratory. Congratulations, Dr. Daniel Cason. Dr. Fall?
Dr. Cason, for pioneering contributions in multi-messenger astrophysics, including seminal work on kilonovae, R-process nucleosynthesis, white dwarfs, and type 1 and 2 supernovae, and for leadership in the application of high-performance computing and astrophysics. Congratulations.
Thank you.
Up next, in the category of Computer, Information, and Knowledge Sciences, Dr. Robert B. Ross of Argonne National Laboratory. Congratulations, Dr. Robert Ross. Dr. Fall?
Dr. Ross, for significant research contributions in the areas of scientific data storage and management and communication software and architectures, and for leadership in major DOE initiatives such as the SIDAC program. Congratulations.
Thank you.
Up next, in the category of Biological and Environmental Sciences, Dr. Susannah G Tringe of Lawrence Berkeley National Laboratory. Congratulations, Dr. Susannah Tringe. Dr. Fall?
Dr. Tringe, for advances in sequence-based studies of microbial assemblies, revealing the roles of microbial communities in carbon cycling, in interactions with plants, and as drivers of methane production, nutrient cycling, greenhouse gas emissions, and water recycling. Congratulations.
Thank you.
Up next, in the category of Atomic, Molecular, and Chemical Sciences, Dr. Christa S. Walton of the Georgia Institute of Technology. Congratulations, Dr. Christa Walton. Dr. Fall?
Walton, no, Dr. Walton, for groundbreaking research on understanding and control of the hydrolytic and chemical stability of porous metal organic frameworks in complex environments, and for its transformative impact on separation science. Congratulations.
Thank you very much.
Now, on behalf of the Department of Energy, congratulations again to the 2020 Lawrence Award Laureates for your achievements and selection for this prestigious award. Members of the audience, please give our laureates a round of virtual applause as we assemble our laureates for a virtual group photo. Laureates, please also give your fellow laureates a round of applause. Congratulations. Thank you, everyone. Now we will have the pleasure of hearing from each of the laureates who have provided us with brief pre-recorded remarks. Now it is my pleasure to welcome remarks from Dr. Etoy.
Hi, everybody. I'm Etoy. I'm a professor at Stanford University and SLAC National Lab. It's my great honor to receive the Lawrence Award. I would really like to thank my students, my colleagues, my collaborators, and the long-term support from the Department of Energy. My lab's main contribution is on using nanoscience for solving the energy and environmental problems, particularly on reinventing the batteries technology. We all know batteries are very important, which enable electric cars, allow you to integrate solar and wind electricity into the electrical grid. My last main contribution is using nanoscience to enable the new materials to significantly improve the battery's performance. For example, we would really like to have the batteries with much high energy store inside a unit per unit volume or per unit weight. In order to do that, we need to use new materials to store a lot more lithium ions to replace the existing graphite anode, lithium metal oxide cathode with much higher capacity materials. However, the volume expansion, structure change, and stability issue of these materials once lithium ions coming in and out cause a lot of problems, which make these materials not possible to be used. In order to solve this problem, my lab has pioneered the nanoscience approach to design the materials to overcome the volume expansion problem, breaking problem, instability problems. Examples include silicon anode and lithium metal anode, which has 10 times higher capacity or more compared to the current technology. We also work on sulfur cathode that also has 10 times higher capacity than the existing lithium metal oxide cathode. The nanoscience approach has been helping to improve these materials tremendously, make them possible to be deployed in the commercial scale down the road. Silicon right now is already started to go into the commercial world. I also help inventing the new chemistry. For example, nickel hydrogen gas chemistry is a very long lifetime one. We reinvent this chemistry for the use of integrating solar and wind electricity into the electrical grid. Overall, I'm very passionate about using the nanoscience approach to solve the problem of energy environment. I hope to continue to contribute to help building our clean energy economy.
Now it is my pleasure to welcome remarks from Dr. Dana Dattelbaum.
Good morning and good afternoon. I'm Dana Dattelbaum from Los Alamos National Laboratory and this year's EO Lawrence Award winner in the area of national security and nonproliferation, joining you from my home in northern New Mexico. I am both humbled and grateful to be honored with the 2020 EO Lawrence Award, and I would like to extend an enthusiastic congratulations to my colleagues being honored here today and a sincere thank you to the Secretary. I wish we could be there in person. The work for which I'm being recognized deals with matter in extremes, or the extreme conditions of pressure, temperature, and dynamic loading. Those conditions are relevant to planetary formation and the origin of life on Earth, as well as being able to predict the extreme states reached in nuclear weapons. Today, I'm being recognized for 3 principal areas of work. First is a body of work in shock physics, where myself and colleagues have provided the data and hydrodynamic modeling constructs for simulating the response of polymers and foams and related organic materials. These materials decompose under the extreme conditions encountered in nuclear weapons, and we have discovered many of the details associated with those chemical transformations and how to model them. Secondly, I have spent much of my career studying how explosives initiate to detonation. This includes their sensitivities and how their microstructures couple to create localization and reactive burn. Following the events of 9/11, I also became an expert in the shock sensitivities of homemade and improvised explosive mixtures, including liquid explosives. Lastly, through the support of such programs as laboratory-directed research and development, we have made great leaps in understanding shock-driven reactive flow in simple molecules that form the building blocks for high explosives. From measurements of the first reactive wave profiles to more recently applying high brilliance X-rays to measure features of reaction products at our DOE light sources, our knowledge of chemistry and extremes is accelerating at an inspiring pace. For over 20 years, it's been quite a ride, as they say, and what stands out to me most is how we within the DOE can bring together the large teams to do the seemingly impossible. It is the people with their diversity of thought and expertise and the large-scale facilities that DOE and NNSA support that make all of this possible. They say sometimes that one's career is a random walk, and while I knew I wanted to work for a government laboratory, my random walk was supported by a team of mentors in the DOE. As a grad student, I was supported by a DOE fellowship and DOE grants at the University of North Carolina, and upon coming to Los Alamos, I transitioned to the National Security Mission Space of NNSA. It is the persistent and unwavering support of the long-term hard problems that makes the DOE able to accomplish what it does, and I have personally benefited from this. In some ways, working at Los Alamos is not so different than it was 75 years ago, and it is not just the beauty of northern New Mexico, but as scientists, we come from all over the world to dedicate our careers to DOE and NNSA missions, and our colleagues become both our friends and makeshift family. Today, I would like to thank some of my key mentors and colleagues that have both inspired me and worked side by side with me in the trenches, if you could use that term to describe all night shifts at a beamline. These include my colleagues Steve Sheffield, Rick Gustafson, Josh Coe, Ralph Menikoff, and the many students, postdocs, and technicians I have worked with, as well as my professional mentors, Deanne Idar, Kim Scott, and Mark Chadwick, and the individuals that nominated me for this award, And finally, I would like to thank my family for their support of my education and instilling in me my passion for science. Thank you.
Now, it is my pleasure to welcome remarks from Dr. Dustin Froula.
My name is Dustin Froula, and I'm a scientist at the Laboratory for Laser Energetics and a professor of physics at the University of Rochester. It is an incredible honor to be recognized by the Lawrence Award for the work we have done with the Department of Energy. The accomplishments that have led to this award would never have happened without the numerous people in my life who have supported me, educated me, and mentored me. It is my wife, Lynette, and kids, Scotty, Addie, and Tori, who make balancing my scientific obsessions with my family time possible. It is my parents, my dad, a second-generation physicist who fostered a creativity from an early age that influences nearly everything I have done, and my mother, who understood how to build confidence in a dyslexic kid who couldn't read and write when entering high school. Together, they set my foundation for success and my drive to continue to ask the question of how it works. My scientific career at the Department of Energy started with an undergraduate research internship at the Lawrence Livermore National Laboratory studying fusion through sonoluminescence. It was during this time I discovered the Scientist Candy Store, an institution where access to instruments allowed its scientists, including students, to follow their unbounded ideas while providing unfettered access to experts on nearly every subject. As a graduate student, I regained access to Livermore through the NNSA-sponsored Graduate Research Fellowship, where I found an advisor and a mentor in Dr. Siegfried Glenzer. It was Siegfried who taught me about Thomson scattering, the key tool that was used in the research recognized by this award. Thomson scattering became the tool that we used to build quantitative understanding of laser plasma propagation and define the parameter space that today bounds fusion experiments on the National Ignition Facility. After 10 years of engorging myself in the Livermore Candy Store, our family moved to Rochester, New York, where I joined the University of Rochester. It was from this new role that we worked to supply the candy store with candy. Primarily working through graduate students and early career scientists, we have continued to develop new ways to use Thomson scattering to advance fusion and to investigate fundamental plasma physics that may someday revolutionize our ability to understand and control plasmas driven by intense radiation. The breadth of our work in plasma physics and innovation in science has been driven by the environment at the University of Rochester, which has largely been set by our director, Dr. Mike Campbell. The Laboratory for Laser Energetics has developed an operation team that is dedicated to getting the details right every time, an engineering team with a drive to meet and exceed the requirements, and a scientific team that can put it all together to solve grand challenge problems. It is this cross-disciplinary approach that has made the research recognized by this award possible. In particular, the discovery of the flying focus, the ability to control the trajectory of intense radiation, and the demonstration of intensities moving faster than the speed of light. It is the individuals who have contributed to this research recognized by this award that deserve the recognition. I am so grateful to be surrounded by so many talented colleagues. And as I move out of my mid-career with this capstone award, I look forward to the continued collaboration with the incredible people in our community that are focused on moving the science missions of the Department of Energy forward. This recognition is a tremendous honor, and I thank you and all of you who have made it happen.
Now it is my pleasure to welcome remarks from Dr. Zaheed Hassan.
I'm Zaheed Hassan. I'm Eugene Higgins Professor at Princeton University. I also do experiments at the Lawrence Berkeley National Lab and Stanford Linear Accelerator Center National Lab, SLAC. So I'm being cited for my work on topological quantum matter and novel fermionic particles. The work involved multiple collaborations between Princeton, Lawrence Berkeley Lab, and Stanford Linear Accelerator Center. I use photoelectron spectroscopy, a technique that works best while using particle accelerators pioneered by Ernest Orlando Lawrence. The technique itself was explained by Albert Einstein, for which he actually won his Nobel Prize. It allows us to explore and discover quantum states of matter in great detail. I have been very fortunate to have a number of brilliant students, postdocs, collaborators, and colleagues. Working with my students and collaborators at Princeton, Berkeley, and Stanford, I discovered a number of quantum matter that are topological in nature and host exotic fermionic particles. The effects we discovered could be the basis for energy-saving electronics, greener technology, and next-generation quantum computing. All of these aspects are important to DOE in line with the mission of DOE. I'm very grateful for wonderful DOE support of my research for many years through Dr. Lane Wilson's program under the Basic Energy Sciences Division. It has been a wonderful journey together with BES. While growing up in a remote part of the world, Bangladesh, as a child, I dreamt about doing research at Princeton or a big accelerator laboratory invented by physicist and Nobel Prize winner Lawrence. Big dreams come true only rarely in life, but it turns out, at least in my case, it did. I'm surprised myself. So my journey has been much like that of a fairy tale story where a little village boy turns into an enchanted prince of some wealthy empire. In this case, it's a scientific empire of many labs. It has been an amazing journey so far, and I have always been grateful for that. So I wish to thank my wonderful students, hardworking postdocs, fantastic collaborators, and great colleagues at Princeton, Berkeley, and Stanford. Thanks to my loving parents for their blessings, and to my wife, Sarah, and the kids for all their love, understanding, and support. Special thanks to Sarah for being my muse and her constant support through thick and thin. Thank you all.
Now it is my pleasure to welcome remarks from Dr. Daniel Cason.
My name is Daniel Cason. I'm a professor of physics and astronomy at UC Berkeley and a scientist in the nuclear science division at Lawrence Berkeley National Lab. I'm so grateful to the Department of Energy for this recognition and for all the support they've given me over the years. The DOE has long been addressing the big questions of how our universe evolved from, a relatively simple soup of hydrogen and helium into the landscape of complex materials and structures around us. And my research focuses on stars, which are main actors in that story. Since the heavy elements in the universe were synthesized in the interior of stars and in stellar demises, such as stellar explosions as supernova and stars collapsing to neutron stars and black holes or colliding. And these reach conditions of extreme density, energy, gravity, magnetic fields, unlike anything we could create here on Earth or laboratories for studying new fundamental physics. I'm fortunate to be working in a time where new developments have opened up new opportunities, new telescopes and gravitational wave experiments detecting transient stellar explosions, as well as advances in supercomputing that have given us orders of magnitude increases in computational power, which is driven in large part by DOE investments in high performance computing. And the main focus of my research has been on using the theory and those computational models to try to understand how physics on the microscopic scale of particles and nuclei play out on the astronomical scale of stellar explosions. And this is already starting to address some key chapters in the story of the origin of the elements. To give one example, when two ultra-dense neutron stars crash into each other, they can expel an exotic cloud of neutron-rich matter into space. And simulations that my group and other groups have done have shown how those clouds can assemble into heavy elements like gold and platinum and uranium and give off a kind of distinctive glow that was seen for the first time just a few years ago by astronomers, the first time that we've been able to see exactly how some of the heaviest elements in the universe came into existence. So there should be much more in the future, more data, more advances in computing, like the next generation DOE exascale machines that are coming online in the future. So I'm so grateful to be part of such a large and diverse community of people that are working in this science. And I'm so fortunate to have been able to work with so many wonderful undergraduate students and graduate students and postdocs who were really the ones that are driving the research forward. And so thankful for the many mentors and collaborators who have helped me and supported me. And finally, of course, I want to thank my family, my parents and siblings, and my wife Simone and children Oliver and Jude, who have been there with me every step of the way. So my congratulations to the other Lawrence Award recipients, and thank you again.
Now it is my pleasure to welcome remarks from Dr. Robert Ross.
My name is Rob Ross. I'm a senior computer scientist at Argonne National Laboratory and the director of the Rapids Institute that is part of the Scientific Discovery Through Advanced Computing, or SciDAC program. My research that led to my nomination for the Lawrence Award has focused on challenges in large-scale data and storage. I think we all realize the importance of data in our lives, from the media we watch to the photos, videos, and messages that we share. But data have special roles in the sciences. Data are generated in huge volumes by supercomputers running simulations, for example, to design batteries for electric cars, as well as by large beamlines exploring protein structures and telescopes probing the nature of our universe. Capturing these data, storing them and organizing them, extracting insights, these are all challenging problems, and the best solutions are often unique to the science in the same way that the theory and codes used in those domains are. Most recently, artificial intelligence, or AI, activities are also having a dramatic impact on research into data and storage, not only because these algorithms are very data intensive, but also because what and how we store these scientific results influences how well the AI algorithms are able to understand those results. Additionally, AI is impacting data services themselves with the potential to make them more effective. On the technology side, exascale computing involves new computing technologies, new scales that bring all sorts of new challenges. In one of my favorite activities, we're developing methods and tools to democratize data service development so that many teams can build tailored data solutions and share components with one another to help each other adapt to exascale more quickly. One advantage of the national laboratories is our ability to easily collaborate with domain scientists, such as the others being recognized today. SciDAC is one program that brings these communities together, and in the Rapids Institute, I lead a team of computer scientists from 13 institutions who are all working with scientists across a wide range of disciplines. We tackle challenges such as managing huge volumes of data, making the best use of new platforms, understanding and visualizing scientific results, and effectively applying AI techniques to their science. These interactions also give us important feedback on our research and let us know what's successful and maybe what's not. Of course, I wouldn't be here today without the efforts of my amazing team at Argonne, great research collaborators, the talented team in Rapids, and the consistent support of DOE program management and Argonne leadership. I am so grateful to have the chance to work with all these people and aid in DOE science, and it's truly an honor to be recognized in this way today. So thank you so much. The first 2 decades that I've had as part of the DOE family have been incredibly rewarding, and DOE science continues to be a very rich source of computer science challenges, and I look forward to many more years of creative problem solving.
Now it is my pleasure to welcome remarks from Dr. Susannah G Tringe.
Greetings. I'm Susannah Tringe of Lawrence Berkeley National Laboratory and the Joint Genome Institute, and I am receiving the Lawrence Award in Biological and Environmental Sciences, something many are not aware the Department of Energy supports. But in fact, many important biological discoveries and innovations have been supported by DOE, including the Human Genome Project and CRISPR gene editing. I first began working on environmental microbiology when my postdoc advisor at Berkeley Lab, Eddie Rubin, suggested that I shift gears from my interest in human genomics that brought me to his group to a project examining DNA sequence from soil. Since all living organisms store their genetic information in DNA, sequencing DNA extracted from an environmental sample could, in principle, create a blueprint for all the organisms found there, sometimes called the metagenome. Yet at the time, most considered this an unwise venture due to the large number of distinct microorganisms found in such samples. And indeed, the existing sequencing technologies were woefully inadequate to the task. But Eddie was excited by the vast untapped genomic potential and persuaded me with his infectious enthusiasm. My initial reports on our project at conferences were met by responses ranging from skeptical questioning about interpreting a mix of data from different genomes to angry outbursts at our audacity in hypothesizing function based on fragmented sequence data. But our early work demonstrated that different environments do indeed harbor distinct genomic signatures, which can be recognized without complete sequencing of all the component genomes. Vast improvements in sequencing technologies, as well as bioinformatics methods in the years since, have dramatically expanded our ability to interrogate these communities to the point where reconstructing complete genomes from environmental samples is now commonplace. By integrating these data with biogeochemical measurements like methane fluxes, we can form specific testable hypotheses about what organisms are performing specific functions and how. It is my hope that this understanding will allow us to enhance natural carbon sinks, grow crops more sustainably, and reduce harm to the environment from human activities. In accepting this award, I'd like to thank all my mentors and colleagues who have advised and helped me, the amazing scientific, technical, and administrative support staff at JGI and LBL, and my family for supporting me through the struggles of being both a scientist and a mom. I'd also like to thank the DOE for supporting the Early Career Research Program, which helped launch me as a scientist, and for supporting user facilities like the Joint Genome Institute, where I've had the opportunity to help advance the research of countless brilliant scientists whose accomplishments far outshine my own.
Now it is my pleasure to welcome remarks from Dr. Christa Walton.
I'm Christa Walton, Professor of Chemical and Biomolecular Engineering and Associate Dean for Research in the College of Engineering at Georgia Tech, and it is such an honor to receive the Ernest Orlando Lawrence Award. I want to first thank the DOE Office of Science for their support of my research, and I also want to thank the experts who carried out the merit review process for this award. I want to thank Julia Kubanik and Tim Lewin for leading my nomination, and I want to thank my collaborators and friends at Georgia Tech, David Scholl and Chris Jones. Georgia Tech is such a supportive and collaborative environment, and I feel lucky to work here. I'm also indebted to the PhD students and postdocs in my research group, both past and present, who have partnered with me and brainstormed with me to carry out my research vision now for almost 15 years. I'm receiving this award for our work in understanding and control of stability of porous materials for separation science. And I'm assuming you don't think about these topics as much as I do, so I wanted to explain a little bit about why this work is important. You can think of a porous material as a kind of a molecular sponge that can be designed to soak up only the molecules you care about. A few examples of how you might use these sponges include air purification systems like chemical respirators, or processes like carbon dioxide capture from power plants. The type of molecular sponge that my group works on is called metal organic frameworks because you make them from metal parts and organic parts. The structures are almost like a scaffolding at the molecular level. They're very ordered and designed with specific shapes and sizes so that they can absorb or soak up the molecules that you're targeting. So the problem is that many of these separations have to work in environments where contaminants like water are present. And with these materials, if you just add some humidity to the system, the structure falls apart. So now you don't have the pores available to soak up the molecules and perform the separation. So my research over the past 10 years has focused on trying to understand this stability issue, looking for solutions and for ways to create more robust structures so that we can design more energy efficient chemical separations. So finally, I want to end by thanking my family for their unconditional support and love over the years, especially my parents and my siblings. I'm a first-generation college student from rural Alabama. My dad's a farmer, and my mom stayed home with my siblings and me. My parents always found ways to encourage my interests, whether it was computer camp when I was 10 or space camp when I was a teenager, and I really wouldn't be here today without them. So I hope now I have nieces and nephews that I'm able to inspire them to choose their own paths and just to know that they can do big things, whatever their heart desires. So given the difficult year we've all just gone through, I want to leave you with a favorite quote of mine. Dr. Marie Curie said, "Life's not easy for any of us, but what of that? We must have perseverance and above all, confidence in ourselves. We must believe that we are gifted for something and that this thing must be attained." So I wish for all of you great perseverance during our continued difficult times, a great support system, just a love for what you do. So thanks again to DOE for this wonderful honor and for the chance to speak to all of you today. Thank you very much.
Thank you to all our laureates for your remarks. Before we conclude today's ceremony, on behalf of the Department of Energy, I would like to extend a word of congratulations to all of you. Congratulations. Now it is my pleasure to introduce Dr. Chris Fall again for final remarks.
That was literally a word of congratulations. All right. Well, folks, that's the ceremony for the 2020 Lawrence Awards. Sincere congratulations to our laureates today. Remember, please, that the award doesn't come without strings, does come with cash, doesn't come without strings. No time to let up on the gas, right? The nation needs you, needs your dedication, your example, not least, and of course the world needs your science and technology. You know, as we finish up here, just one point of personal privilege. This is my final event, and among my final official acts as director of the Office of Science. And I can't think of a better way, frankly, to end my time here than with one of my favorite parts of the job, as I said before. It's been a tough year for all of us, and what a joy, really, to celebrate your achievement, human achievement, really, like this on behalf of the nation and the world. So thank you very much. Congratulations again, and please, everyone, stay safe.
Thank you.
Thank you very much, Dr. Fall, and thank you to everyone who has attended the ceremony today. This concludes the ceremony proceedings. Be well.